Hello, everybody. Today, I would like to introduce the talk by Professor Andrei Vesnin from the Tomsk State University, Novosibirsk State University, and Higher School of Economics around right-angled hyperbolic polytopes. So please.
Thank you very much for very kind invitation. It is a big pleasure for me to give a talk in this beautiful seminar. And I will try to talk about combinatorical and geometric aspects of theory of hyperbolic manifolds and hyperbolic polytopes. So let me start with some outline. Firstly, I want to tell you something about hyperbolic three-dimensional space and special class of polytopes, besides that all dihedral angles are pi over 2. So I call these polytopes right-angled. So all dihedral angles equal pi over 2, and all plane angles also pi over 2. After that, I would like to tell how we can use these polytopes to construct three-dimensional manifolds. And I would just mention about it because it seems interesting since we use a four-coloring approach, similar to classical coloring of maps. After that, I would like to tell something about graph theoretical invariance of fullerene graphs, which belong to a class of which I consider. And finally, I want to formulate some conjecture about the relation which we found between combinatorics and geometry, and I will tell it at the end of the talk. So if you have any questions, please stop me, and I will be glad to tell more if you will need. So firstly, let us discuss hyperbolic three-dimensional space, or in Russia call it Lobachevsky space, and special class of polytopes. So let me briefly call about two-dimensional situation. If you consider two-dimensional surfaces, so classification of closed orientable surfaces is known. It's just sphere with a few handles. So sphere, torus, and so on. And for each of these surfaces, we can introduce corresponding geometrical structure. So it will be spherical, Euclidean, or hyperbolic structure. So we have a spherical geometry for the sphere, we have flat geometry for torus, and for remaining surfaces, we have hyperbolic geometry. And I would like to go from dimension 3, but first of all, I would like to mention that to construct surfaces with geometry, right-angle polygons are very useful. So one of the most famous examples in dimension 2 is how to construct a torus. You can start from Euclidean foregone, and you just identify opposite sides according to the rule presented in the figure. In the first step, you get a cylinder. After that, you glue boundaries of cylinder, and finally you get a torus. So you can do it by isometries, and you see we identify just the sides of Euclidean polygons. So we can do it by isometries. So you can consider that we are working with a group which give identification of opposite sides, and we get the torus as a quotient space. And we automatically get the geometry on this quotient space. The geometry came from universal chaos, so from our foregone. And today I would like to show a similar approach in dimension 3 in hyperbolic geometry. So why it is interesting? Maybe first I just recall you something about a very famous geometrization conjecture, but now this is a geometric theorem. So conjecture was posted by Wiener and Thurston, and geometrization conjecture states that any closed orientable prime free manifold contains a disjoint union of embedded two torus or enclosed bottles, such that each connected component of the complement admits a locally homogeneous Riemann metric of finite volume. So, briefly speaking, we can cut our three-dimensional manifolds in geometrical pieces. And these geometrical pieces belong to a family of 8 so-called torsion geometries. So it's Euclidean, spherical, or hyperbolic, or two product geometries, so sphere times real line, or hyperbolic plane times real line, and 3 more exotic geometries, so universal cover of a group SL to R, so nil geometry and solid geometry. And today I will be mostly concentrate on hyperbolic three-dimensional space. So we are interested in these manifolds because they are very wide class of geometrical pieces for general family of three-dimensional manifolds.
I'm sorry.
Yeah.
So do we have to remember this statement? Because I don't remember what is a prime manifold, for example. But would it be important for the rest of the
It's
talk?
not important. Just to give you some general picture.
Okay.
So it's very famous Thornton geometric conjecture, and Perumal was awarded Fields Medal for solving this conjecture. So it's just general context we are talking about. Okay. And we will talk mostly about concrete three-dimensional space, about hyperbolic space, and about hyperbolic manifolds. And there are few nice models of hyperbolic space, and today I will mostly use hyperbolic space modeled in a ball. So we have a ball, and two-dimensional sphere is the boundary of this ball. It's a point at the absolute of our space. There's four points at infinity, and planes in this geometry just semispheres orthogonal to the absolute, and lines just lines passing through center, or semi-lines orthogonal to the absolute. So this model which I use for pictures mostly, and so I don't need to draw exactly geometry or metric, so we don't use really metric. So this is one of the famous model of geometric hyperbolic space. And what is interesting, what we have in free and high dimensional situation, this is the following the most of rigidity theorem. So if we consider n-dimensional hyperbolic space, so we can normalize the constant curvature by -1, and let's consider group G, which is a discrete as a group, and suppose it's fixed point free, so it's acting without fixed point. And this group is a group of isometries of our space. So we can consider the quotient space, the quotient space under this group action. And since you consider isometries, the quotient space also will get a constant curvature metric, and will be locally symmetric to a hyperbolic space. And we obtain a manifold since we act in without fixed points. And the quotient space we will call a hyperbolic manifold. So hyperbolic usually means that you obtain its the quotient of discrete group action on hyperbolic space. And comparing with dimension 2, dimension 3 and bigger, they are very rigid in the sense of the following most of theorem. So suppose you have two hyperbolic manifolds which have finite volume, and suppose they are homomorphic, so their groups are isometric. Then a theorem states that there is isometry between these two manifolds. So broadly speaking, if you have two manifolds, and you know that you can introduce hyperbolic geometry on both of them, so any homomorphism means isometry. So any isometry invariant, for example, geodesic spectrum or volume or something like that, will be topological invariant. So in this sense, class of hyperbolic manifolds is very specific, and we will discuss volumes of some polyhedra, and we'll construct manifolds from this polyhedra, and because of this theorem, volumes will be topological invariants of our manifolds, not just geometric.
And can I ask you a question? What happens for dimension 2?
For dimension 2, it's not true.
Okay. So there is no
such kind of rigidity. Yes.
Okay.
And the question about the examples of such manifolds is quite old. And if you look at Felix Klein's book, call it Not Euclidean Geometry, it was published in the last of 19th century. So he mentions there that there are no examples of compact hyperbolic free manifolds at that time. And the first examples appeared in the 20th century. And the first example was constructed by Gisekin, he's student of Max Den. He constructed a compact non-orientable manifold. And after that, in 1931, Frank Loebel constructed the first example of a compact orientable manifold. And after that, Weber and Seifert constructed an example of compact orientable, so-called dihedral hyperbolic space. And in all these constructions, also uses some polyhedra and defining the group action using this polyhedra. For example, in the case of Gisekin, he used the tetrahedron in hyperbolic space. Loebel used few right-angle polytopes, and Weber and Seifert used the dihedron in hyperbolic space. So this is one of the reasons why I want to tell you about hyperbolic manifolds which are constructed from right-angle polytopes. And we have very interesting results, also some rigidity theorem, which was proved by Andreev in 1970 about polyhedra in hyperbolic space. Again, starting from dimension 3. So suppose we have bounded acute angles. So acute means that all the angles are at most pi over 2 polytope in a high-dimensional hyperbolic space. Then it is uniquely determined by its combinatorical type and by its dihedral angles. And moreover, he proved necessary and sufficient conditions for existence such kind of polytope in dimension 3. And today we talk not about general case, but about specific case. So we consider it to be the polytopes, which call it Coxeter polytopes. So such as all dihedral angles of the form pi over k, the k is integer, or right-angle polytopes, they are all at angles pi over 2. And case of pi over 2 was first considered by Alexey Vasilyevich Pogorelov, a famous Russian academician. I suppose many students know his textbooks on analytical geometry and the physics of geometry. And in the first issue of Jean Mathematical Notice in 1967, he published a paper about right-angled hyperbolic polytopes. And if you consider a combination of two theorems, Pogorelov theorem and Andreev theorem, we can give a characterization of such a polytopes in hyperbolic space. So first we could give a definition. So let's consider combinatorial polyhedron, and we call it Pogorelov polyhedron if any vertex is the free valent, so it's incident to exactly 3 edges, and if any prismatic circuit which separate two faces of our polyhedra intersect at least 5 edges. So let's call it Pogorelov polyhedron. And from Pogorelov and Andreev theorem.
Sorry, excuse me. What is the prismatic circuit?
I will give you a picture just a minute.
Okay.
So you have a polyhedra, and you consider the curve on the surface, and you assume this curve separate two faces, similar to prisma.
Okay.
Something like that. I give you a picture.
Okay.
And from these two theorems, we obtain the result that combinatorial polytope can be realized as a bounded right-angle polyhedron in three-dimensional hyperbolic space if and only if it is a Pogorelov polyhedron in combinatorial sense. So everything depends on combinatorics here. And this example of prismatic circuit, so let us consider polyhedra, which presented here is free valent, and all faces are at least pentagons. And you can see the blue curve. It separates top and bottom, for example. but it intersects only 4 edges. So it's an example of a prismatic circuit which you don't like. So it's a very bad example. And the simplest
Excuse me, can you
sorry?
Excuse me, can you return? I don't get the definition of prismatic circuit.
Really, I didn't give a definition. On the slides, I just tell that suppose you have a polyhedron and a closed curve on the surface of a polyhedron is prismatic circuit if it separates 2 faces of the polyhedron.
Okay.
Okay. And this is example. So you have a curve, the closed curve on the surface of the polyhedron, and it separates really not just 2, just separate many faces, but the curve intersects only 4 edges.
And when you say separate, you mean strictly separate, so that it does not touch these faces either.
Yes, strictly. Yes. And the simplest polyhedron of such type is the Dicahedron, and I use the Boyle model for hyperbolic space to draw it. So it's smallest in combinatorial type. So in hyperbolic geometry, we cannot have 4 gons if polyhedron is right-angled. So any face should be right-angled, so it's at least pentagon. And the large class of examples are fullerenes. And just I would like to discuss a little bit later fullerene, so I give you some reminding about it. So as a fullerene is just polyhedral molecule made from carbon atoms, and the age corresponds to bonds. So the most symmetric and most famous is fullerene with 60 vertices presented here. And as a graph, it's just a planar graph with prevalent vertices, and each face is pentagon or sexagon. And fullerene is a particular class of polyhedra. Let me consider some family, which I introduced it many years ago, and its family generalized the Dicahedron. So just a projection of the Dicahedron. So we have a picture, we have pentagon and as a top bottom and pentagon as a bottom face. Sorry, so top face and bottom face are pentagons, and you have 2 levels of pentagons around it. And let us generalize this idea and consider 6 gon on the top and 6 gon on the bottom, and again 2 levels of pentagons between them, and so you consider it for arbitrary n. And you will get family of polyhedra with 2n plus 2 faces, and it's easy to check by Pogorelov's theorem that this polyhedra can be realized as right-angled polyhedra in hyperbolic space. And I call it Löbel polyhedra because of German mathematician Frank Richard Löbel, who used one of these polyhedra to construct his original manifold. And this is pictures of this polyhedra in three-dimensional space. So you have angle on top and angle on bottom in two levels of pentagons. Okay, I suppose clear. And since we are in hyperbolic space, you can ask about the volumes of these objects. So volumes can be calculated in terms of the Lobachevsky function. So it's graph of the function, it's periodic, and this odd function. And this looks as kind of de-logarithm function. It's called Lobachevsky function by John Milner in his famous paper published in 1982. And using this function, we usually can calculate volumes of hyperbolic polytopes. So it's not so easy expressions. For example, in the case of these Löbel polytopes, the volume formula looks like this one. So you have a combination of Lobachevsky function calculated in various points. So depending on n, angle top and angle bottom in our family, so you have parameter theta n, and we take a linear combination of Lobachevsky function calculated in special points. So we know a lot about this family, and you can ask what about the general family of bounded right-angled polyhedra in hyperbolic space. And let me introduce two kinds of moves for manifolds for polyhedra of this class. So first move is composition, and is decomposition. Suppose you have two combinatorial polyhedra, and suppose both of them has k-gonal faces, say F1, F2, and F2, and you consider just a composition or connected sum of two polyhedra along these faces. It's just combinatorically. So you have the same k-gonal faces, and you combinatorically glue this polyhedra, and the result proved by Inoue is the following. So if you started from a right-handed polyhedra, then the resulting polyhedra also can be realized as right-angled. So not just combinatorical gluing, but also geometrical gluing. And another move related with the local operation, it's removing or adding H. Suppose you have a right-angled polyhedra and you have some H, denoted by E here. So you can remove this H, and from original polyhedra you get a new polyhedra. So there was N1 gone, and 2 gone, and 3 gone, and then 4 gone. So there will be 1 gone less, and new number of H's will be N1 minus 1 and 2 minus 1, and it will be the new phase created from 2 phase N3 and N4, and it will be N3 plus N4 minus 4. So we remove it H, or we can add H in similar position. And again, this operation is just combinatorical, but we can prove geometric results. So if you start from right-angled bounded polyhedra, so Pogorelov polyhedra in our terminology, and if these faces are big enough, so it has this at least 6 sides, then a new polyhedron again can be realized as right-angled bounded polyhedra. And I would just want to mention that adding of H was also known in chemistry. It was called the Ender-Kroto move for fullerene case, and Kroto is one of 3 persons who got a Nobel Prize for fullerene. So it's natural move also for fullerene in chemical context. And what is a nice result related to these moves? The theorem was proved by Inoue. So suppose you have P0, which is right-angled bounded polyhedra in a hyperbolic free space. Then there exists a sequence of unions of right-angled hyperbolic polyhedra, P1, PQ, such that each new set obtained from the previous set by decomposition or H removing, and a final set is a union of label polyhedra, the particular class which we just discussed. So you can decompose your polyhedra monotonically to the simplest pieces. And for these pieces, we know volumes already. And we know behavior of volumes, so the volume decreased according to this procedure. And it gives a way to prove that the Dicahedron really is the smallest volume bounded right-angled polyhedron, and the next is also from family of Rebel, is the number 6. And a few years later, just in last year, he tabulated 825 bound right-angled polyhedra, so Pogorelov polyhedra, and he uses this composition and adding H or removing H to construct them. So he tabulated until volume 13.4203, and I just illustrate a little bit his approach. So you can start from polyhedra, which has 6 gonal faces. So for this L6 from Lobel family, and you can add new H to these 6 gonal faces. So to the top or to the bottom. Up to symmetry, you can choose a top, and the new polyhedron, you just add a new H, which is blue here, and now you have more 6 gonal faces. So you can apply adding H now to these faces, and you can continue the process, and you now we added new H here and new H in this position, so you obtain more 6 gonal faces, and you can continue this process, and step by step you can start a new polyhedra, which are Pogorelov polyhedra again, and you know that in this process the volume increase. And I would just want to mention that the decomposition of regular polyhedra is not unique. So, for example, this polyhedra on the right can be obtained in two ways. So you can start from L6 and apply 3 moves of 18H, or you can start from L7 and do just one 18 move. And as I told, everything can be considered from combinatorial point of view, since we see fixed dihedral angles. So I want to mention that if you know number of vertices of your polyhedra, so you can estimate volume. And a very nice result was proved by Christopher Atkinson. So if you have Pogorelov polyhedra, and if you know that it has V vertices, so V is the smallest number of vertices corresponding to the dodecahedron. So the dodecahedron has 20 vertices. So the lower bound looks like this one, and upper bound is like this one. And there is a constant denoted by V8. This is 8 Lobachevsky function calculated in 0.504, and up to 15 decimal, this is 3.66, and so on. This is volume of ideal regular octahedron in symbolic space, which is some constant.
Sorry, so this VI, V3, and V8, did you define them for this?
Sorry. V3 is another constant. This is about 1.1.
Okay.
Sorry, it's the volume of ideal regular tetrahedron. Sorry.
Okay. And all of these VIs are volumes of certain polytopes?
Yes.
Okay.
So this so V8 is about 3.66 and V3 is about 1.01. Also, V3 has expression in terms of Lobachevsky function. And just recently, we little bit improved this result. So if you know first polyhedra, this is dodecahedron. Also, we know the second with 22 vertices. And if you consider the case when the number of vertices is at least 24, so you can improve a little bit upper bound. So you can obtain V minus 14 instead of V minus 10. And another result in direction is the following. So if you have two angular faces, so you can find the upper bound, something like that. So number of vertices minus this N1 and N2. There is your polyhedra have angular faces. So it gives us idea that if you have very big faces, I mean maybe 7 gons or 10 gons, so you have a better bound. So this example that you can bound geometrical parameters starting from combinatorics. And this is a picture with distribution of volumes. So blue point correspond to volumes of polyhedra, of Pogorelov polyhedra. Red point correspond to this family of regular polyhedra. And you have an upper bound, you have a lower bound. So this upper bound, according to Atkinson's theorem, and we improved it a little bit. I mean, it's now it's better, but lower bound is still not so nice.
Can I see the previous estimate? Excuse me.
Yeah. Sorry.
Can I see the? Yeah. Okay. Thank you.
It's just picture where represent real volumes and bounds.
So would you conjecture, or is there a conjecture that says that Liouville polyhedra minimize the volume for
No, it's not true. The example is not true. For example, for 22, it's not the smallest one.
Oh, okay. On the picture, it looks like it.
It's in too many points.
Yeah. Okay.
It's very close to minimal, but it's not really the smallest one, unfortunately. Okay. And I give a picture of for the case with 24 faces. So the minimal volume is correspond to this polyhedron. So you see that it's not fullerene. There are some faces which are quite big. I think that's about 8 gon. And this is minimal volume, and this is the maximal volume for 24 faces. So it is fullerene, so only 5 gons exist gons. It's just a projection of this polyhedra. So on the projection, the 6 gons presented by green color and pentagons presented by yellow color. And also exterior face is a pentagon. So for each family, we can find minimal volume polyhedra and maximal volume polyhedra. And we know also bounds. And why we're so interested in these families, because we can know how to construct three-dimensional manifolds from Pogorelov polyhedra. And it can be done using colorings. And I want just to give a brief description. So
can I ask one more question? I don't know if there will be some things on graph theory later. You said something, but I just wanted to understand combinatorially, just speaking about the hyperbolic polyhedra. Is there the same correspondence between planar graphs and polyhedra in 3 dimensions, or polytopes in 3 dimensions in H3? That every 3 connected planar graph can be
of course.
realized. So it works just the same, right?
Yes.
And is there a nice studied class of planar graphs which correspond to right-angled polyhedra? I mean, you described it using these 2 operations, but is there another characterization, or is it some famous class of planar graphs? Or?
Yes, there are some more results in direction. So, for example, Collier-Havets generalized in our approach, and he proves that it's enough to just to glue the Dicahedron and to obtain this family. So the question is, what is minimal generated set? And this question we'll discuss it here.
Okay.
Very interesting result obtained by Collier-Havets, for example, in this direction. Okay, so now we have polyhedra, and I would like to tell you that we can construct manifolds. And if you consider a polyhedra, bounded right-angled polyhedra in hyperbolic space, so Pogorelov polyhedra, so we can consider the group generated by reflections in its faces. And if you look at picture of the Decahedron, you can see that for any vertex, we can consider stabilized in the group generated by reflections, and this group is just a abelian group generated by 2 elements. So it's algebraically just Z2 plus Z2 plus Z2, I mean 3 copies of 2-element groups, and each 2-element group corresponds just a reflection in the face incident to our vertex. So it's stabilizer consisting of 8 elements, and our aim is to find torsion-free subgroup in this group G. If you want to obtain manifold, so we're interested in a group which acts without fixed point. So algebraically, it means that your group is without torsion, without elements of finite order. And it can be done. So let us consider this 8-element group as a vector space. So we can think about elements as vectors, for example, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, and so on. So if just a remark that if you take these 4 elements, so any of three of them are linear independent in these groups considered as a vector space. And if you want to find a subgroup of group generated by reflection, which is torsion-free, we can consider epimorphism to these element groups. And suppose the epimorphism is such that we send any generator of the group of reflections to one of these elements, A, beta, alpha, beta, gamma, or delta, in such a way that no 2 neighbor generator go to the same element. So it is correspond to usual coloring of the map in 4 colors. So under this condition, we'll get that kernel is torsion-free and does contain rotation reversing elements. And we can apply it for any right-angled bounded polyhedra. So if you consider the group generated by reflections, and if you consider such a epimorphism that any generator go to one of the 4 color, and any 2 adjacent phase get different color, we get a kernel which is torsion-free. And the quotient of the hyperbolic space by this kernel will be closed to the hyperbolic manifold. So to define such kind of epimorphism, really we need just to give a for coloring, as usual coloring of the map. So our polyhedra, just usual polyhedra on the sphere. So this is just a general case of for coloring problem. Also our graphs are free-variant graphs. And we construct the manifold from 8 copies, since our subgroup is of index 8. So I just give you some pictures. So if you start, for example, with the Dicahedron and consider 3 generators G1, G2, G3, the reflections in faces incident to vertex V. So we can glue images of our dodecahedron on the stabilizer of the vertex. So on the first step, we glue 3 new polyhedra around this vertex. So this union of 4 copies. And after that, we can add 3 more. So this union of 7 copies. And finally, you'll get union of 8 copies of our original dodecahedron. And you obtain a manifold by pairwise identifications of faces of this new polyhedron. So this picture, due to Vladimir Bulatov, he produced a lot of nice pictures of hyperbolic geometry. You can go to his homepage. Okay, so we start from arbitrary Pogorelov polyhedra, and from 8 copies we can obtain a manifold.
Excuse me, can you maybe go through this example a little bit slower, because I personally get lost. How do we? So how on this example, what would be the for coloring?
So we start, for example, with dodecahedron.
Yeah, yeah.
And we suggest some for coloring.
Yeah.
The usual coloring. So this coloring define a epimorphism from the group generated by reflections to the group of 8 elements.
Yeah.
You just think about coloring just as element of this group.
Yes.
You can think your coloring just alpha, beta, gamma, and delta.
Yeah.
So coloring just the language to define a group homomorphism. And the property is, if you start from good coloring, I mean coloring in the sense of graph theory, so the kernel will be torsion-free. So there are no element of finite order in the kernel, and thus there are no rotation revising elements. So any isometry preserve orientation. So we can find the manifold, which is a quotient by the kernel. But our kernel is a group of index 8, since we consider it the homomorphism to the 8-element group. So our manifold will be glued from 8 copies of original dodecahedron, for example.
Mm-hmm.
So I just want to illustrate how you can start gluing. Firstly, you obtain union of 8 copies. And after that, coloring, you define the gluing of faces in pairs.
Mm-hmm. Okay.
So you obtain this polyhedron, and depending on the coloring, you will get different gluing of faces of this polyhedron. And finally, you get a quotient space, which is a manifold. And a classical example constructed by Lobel in 31 can be described in this language. He uses nice description, but now we can present this description. So we can start from polyhedron with number 6, so Lobel polyhedron number 6. So you have 6 gonal top and 6 gonal bottom. And you can consider coloring in 4 colors, alpha, beta, gamma, like here. So alpha and beta and gamma and delta, they're colored. And if you consider homomorphism corresponding to this coloring, you obtain manifold which Lobel constructed in 1931 by another method. But you can do it with any right-angle bounded polyhedron. And a little bit more about graph theory. So in some cases, you can have Hamiltonian cycles on a polyhedron. So there is a notion of hyperelliptic manifolds. we say that any dimensional manifold is hyperelliptic if there is such involution that the quotient by this involution is homeomorphic to sphere. And this notion came from theory of Riemann surfaces. And jointly with Sasha Mednik, we proved the following result. So if you start from Pogorelov polyhedron, and again, the G group generated by reflections, and now assume that our polyhedra has a Hamiltonian cycle. So graph of this polyhedra has a Hamiltonian cycle. Then there is a subgroup of index 8 in our group of reflection, such that the quotient by this group is Hamiltonian, this hyperelliptic manifold. So it's homeomorphic to a three-dimensional sphere, but there is some singularity which gives us not a link. And I present you example how to find it. So let's consider the same polyhedra as Löbel, but consider another coloring. So we have a polyhedra with 14 faces, and we'll just consider Hamiltonian cycle with the edges of this cycle numerated by numbers from 1 to 24, this orange number, they numerate Hamiltonian cycle. So Hamiltonian cycle split surface of our polyhedra into parts, so we can use two color for each part, so alpha and beta color for one part, and the gamma and delta color for another part. So we can start from coloring of faces. It's induced coloring of edges. So the color of the edge just the sum of colors of faces. So this is an example of Hamiltonian coloring corresponding to Hamiltonian cycle, and we can redraw the Hamiltonian cycle just a circle. So we get a picture like this one. So the edges which belong to Hamiltonian cycle and some extra edges. And now we just consider the double of black edges. So you'll get a link like this one. So there were some edges inside the cycle and outside the cycle. And we consider two-fold coloring now. So for any black edge, we have one edge inside the cycle, inside the disk and outside the disk. So finally, you get 12 components. So you'll get a link with 12 components, and the meaning of this link is the following. So our manifold is a two-fold branch covering of the sphere, and branching set is exactly this 12-component link. And this link formed by edges which didn't belong to Hamiltonian cycle. So you can use the knot theory or link theory to investigate these manifolds too. And as I already told, you can apply coloring to any Pogorelov polyhedra and obtain many such kind of examples. And the natural question to ask about distinguishing of these manifolds. Suppose you use a different coloring, or you take different polyhedra. So when polyhedra and coloring give you the same manifold, and then the very natural answer was obtained by Viktor Buchstaber and Taras Panov. So they proved that if you have such construction, suppose you have manifold n and manifold n prime, where m is obtained from Pogorelov polyhedra P by coloring phi, and m prime from Pogorelov polyhedra m prime using coloring phi prime. So these two manifolds are diffeomorphic if and only if the corresponding pairs of polyhedra plus coloring are equivalent. So polyhedra combinatorics are the same, and colors are equivalent. Up to symmetry of polyhedra and up to renaming of colors.
Okay.
And the proof is quite complicated in the sense it's not inside this combinatorial approach. So they use it very nice method from modern theory called it toric topology. So they use it some rigidity about moment angle manifolds. So they prove that manifolds are the same if the corresponding homology rings are the same. So it's out of our topic now. But you can find the paper published in the Russian Mathematical Surveys. So now we have a complete description. So we obtain different manifolds if and only if colors are not equivalent. So if you want to obtain many manifolds, you just take different colors.
Excuse me. So which suggests that the number of these manifolds grows very quickly, because I would imagine that the number of colorings is exponential in the number of bases.
Yes. If it is a huge graph, so there are many colorings, of course. It's interesting relation with the Thurston-Jurgensen theorem about volumes of free manifolds. It is known that if you fix the volume, so for given a value of volume, or a finite number of hyperbolic free manifolds with given volume. But this construction gives you examples of manifolds which it can give examples when this number is arbitrarily large. So you can construct as many as you want. You know it is always finite, but you can obtain many examples. And now I want to go to some graph theory. It's related to other approach to the same object. And I want to discuss a little bit about the quality Wiener index of fullerene graphs. And this is quite interesting in context of chemical informatics. I just refer to the recent paper about drug design. And in this paper, there are classification of chemical descriptors used for design of drugs. And there are also classified chemical descriptors in different classes corresponding to methods and the approaches. And among so-called two-dimensional descriptions related to structural topology, you can find a Wiener index and other indexes as Balaban index, Randic index, and so on. So usually in chemistry, they call it index, but this is just some invariance related to the metric of the graph. So I want to spend a few minutes in discussion of Wiener index. So it's called in honor of American chemist Gary Wiener. This picture of him, and he wrote a very nice paper. It was published in 47 about structural determination of paraffin boiling points. So the general concept in chemistry is like this, like the following. So structure determine chemical properties. So if you have something with very close structure, so you can expect that chemical properties also very, very close. And in this paper, Wiener defined the following invariant of graph, which now call it Wiener index. Suppose we have a graph, a finite connected graph, and we will this set of its vertices. And you consider pairs of vertices, and you consider distance between them, just not minimal number of edges between them. The distance is the set of edge chain. You just take some of all pairs. And he observed the following. So if you take very simple graph, corresponding, for example, to Bhutan, so you have 3 atoms of carbon and 10 atoms of dihedral. So usually in the fullerene graph, people draw only carbons. So there are 2 structural isomers. So number of atoms is the same, but graphs are different. So one isomer is G1, so N-butan, and another is G2 is a butan. So you see there are 4 vertices, but the graphs are different. And Wiener observed that if you calculate his Wiener index, so you consider all pairs of vertices and you calculate distances. So here you have the distance equal 10. So you have 3 pairs of vertices with distance 1, 2 pairs with distance 2, and 1 pair with distance 3. You just see it from this picture. And for isobutan, the Wiener index equal to 9. So this parameter distinguishes 2 graphs very, very easy. And in this paper, Wiener observed that the Wiener index is closely correlated with the boiling point of paraffin, so graph chemical structure with such structure formula. And I was just observed that it was 47, the same year when Norbert Wiener introduced his cybernetics. Okay, so this Wiener index introduced by Harry Wiener, and more exactly, here the relation which he found is the following. So the boiling point for paraffins is a linear combination of Wiener index and some another index called it P is polarity. So polarity is just a number of points of carbon atoms on distance free. So if you take this C7H16, so you see that there are pairs on distance free. This vertex 1 and vertex 4, this first pair. There's 1 and 7 on distance free, and 2 and 5 on distance free, 5, and so on. So for this graph, polarity equal to 6. So he observed that the chemical properties of this chemical structure depends on very simple structural parameters. And nowadays,
sorry, can you again say what is this polarity? So number
you can see the vertices, and you calculate how many vertices on distance free.
Okay.
For example, distance between 1 and 4 just
and all these bonds are that you draw is carbon, right?
Only carbon is drawn.
Okay.
Usually in fullerene only carbon atoms are drawn.
Okay. And
because for H you can get a picture automatically.
Okay. And
just terminal points.
And
so only carbon, so just you can see the vertices of the graph on distance free. You just count how many.
And just out of curiosity, so the two Wieners are not related, or the two Wieners that we had on the previous slide, the Norbert.
No, they're completely different. Yeah, of course.
Okay, so they're not related.
Gary Wiener and Norbert. At least I don't know about personal relations. Okay. I just want to mention this is the same year. And nowadays there are many papers about Wiener index, people who are working in chemistry, and in particular, this Wiener idea gives us a polling approach to study graphs. So suppose we consider just a vertex, and we are interested in parameter of a vertex. So transmission of a vertex for connected graph is just sum of distances from this vertex to other one. So we fix vertex V, and we consider vertex U, so all vertices of our graph, and can calculate distances from our vertex to another one. And this closely related with the Wiener, so it's just 1/2 of sum of all transmissions. And there is a notion of transmission irregular graph. So it's such a graph that you can distinguish all vertices by transmissions. So for all vertex, their transmissions are different. So there's some graph invariant which give you possibility to distinguish all vertices, and I just want to show you a picture for this tree with 7 vertices. So consider such a graph, and there are numbers of vertices, and there are values of transmission. For example, for vertex number 1, the transmission is equal to 10. So it's on distance 1 with vertex number 3, with distance 4 and so on and so on. You just calculate distances to other vertices. So for 1 you will get 10. For vertex number 2 you'll get 11, and so on. So you'll get the transmission different for all these vertices. And people call it the Wiener complexity of the graph, the number of pairwise different transmissions. I don't think that complexity is a perfect word to use here, but this, somebody defined it as a Wiener complexity.
Does it have any chemical meaning? This
I don't know, but people consider it for a different class of graphs, really, because this is just a tree, and I just mentioned that the maximally possible value is just number of vertices. For this graph with 7 vertices, its complexity is just equal to 7. Okay. So for each vertex, you have a separate, you have different values. And recently, Alisa Desh and Klavzar, they constructed families of trees of odd order with this property. So any vertex can be distinguished by transmission. So on the previous slide was just example for 7 vertex tree, but they found infinite families, and they asked about the transmission regular graph for various classes of graphs. And my co-author Andrei Dobrynin, he found many examples in classes of trees with even orders, even order class of 2 connected graphs or 3 connected equivalent graphs and so on. And we are interested to find a transmission irregular graph in the class of fullerene graphs. And we calculated a lot, and I report to you about our calculations. But firstly, I just say that among fullerene graphs, there are also some special subgraphs, call it isolated pentagon rule graphs, so IPR graphs. So it's such a graph that no 2 pentagons are adjacent. So you just look at the picture. So there are 2 pictures of graphs with 80 vertices. It's just projections of the plane. And you see there are 12 pentagons. So one pentagon is just an exterior region, and another 11 just yellow pentagons on the left and the yellow on the right. And both this graph has the property that no 2 pentagons are adjacent. So people say that this fullerene satisfies the isolated pentagon rule. So they call it IPR fullerenes. And many questions about fullerenes also considered for this particular subset of IPR fullerenes, and also generation of this graph was done by Brickman and McKay and Belgur, and they generated all fullerene graphs and IPR fullerenes, and just a number of graphs. So you have V number of vertices, number of faces is just V divided by 2 plus 2. This follows from a yearly formula for polyhedron. So for V equal 20, just one such a fullerene is dodecahedron, and for any even number of vertices except 22, there are fullerenes. And this is the growth of these numbers. It grows very quickly, and you can go to Brickman homepage and find these tables of fullerene generated by his program. So there are a lot of examples known, and this fullerenes, and inside this family, IPR fullerenes. So we take these graphs and we try to find interesting examples which are transmission irregular, and we calculate up this graph up to 216 vertices. And unfortunately, we didn't find any transmission irregular fullerene graphs in this family. So we checked hundreds of millions of graphs by computer, and there are no such example. And I just show what we obtained. Well, the question is still open. So the best what we found is the following. So if you can see the difference between number of vertices and Wiener complexity for this number, so the best example which you found correspond to the 140 vertices. It's here. So difference equal to 9. So we're close to 0, but not 0. So up to this number of vertices, we didn't find example. So it's still open problem. But if you consider another invariant, not the Wiener index, but some modification of Wiener index, we found some interesting example with such a property, and this can be found in our paper.
Sorry, one more question. So this IPR fullerenes from the graph theory point of view are just planar graphs with faces that are only pentagons and hexagons and no two adjacent pentagons. And that's it. So all such graphs are fullerenes.
Yes, yes, exactly.
Okay. And is there a way to randomly generate such a graph? Is there anything
people just tabulated them.
No, I mean that if you want just to prove this conjecture, you may take a very large number of vertices and then take a random such graph and then make
possibly, yes,
statements.
Possibly. But it's okay. Just let me give you a picture about the distribution. So suppose we consider graphs with 196 vertices. So this is a picture of distribution according to Wiener complexity.
Okay.
So this is the values of Wiener complexity. So you see in the middle there are a lot of graphs.
Okay, so normally it is concentrated around something
like that,
which is far from zero.
So I suppose if you start with a random generation, you will be not lucky.
Okay.
I don't know. Okay. So for this 196 vertices, there are 177 millions of graphs. So it's a lot. Okay. So we started to work with Wiener complexity, but really we calculated the Wiener index on the way. So finally, I want to observe about the relation between Wiener index and hyperbolic volume. So during our calculations, we calculated Wiener index for this big amount of fullerenes, up to 260 vertices, and we check it when we get a maximal Wiener index, the fixed number of vertex. And we recognize that these graphs, they look at as a nanotube with the two cups on the left and on the right. It was the structure of such a graphs. And okay, so maybe the more nice picture is a journal where our paper were published in. This is just a cover of the journal. The journal produces this picture. So we have a nanotube and we have two cups on the left and on the right. There are 4 types of cups, and we classified. I mean, the computer we saw these types. So there are only 4 types. So on the left and on the right, we have the same caps. And they are of type A or type B or type C or type 12. So the collection of 6 pentagons. So we have a hexagonal tube, and on the left and on the right, we have 2 collections of pentagons. The type A, so there are, among all classes of graphs, so totally there are 93 families. I mean, for fixed number of vertices. So you see how many examples of each type. So for this type, we see that the Wiener index is maximal. And also, if you fix it caps, so tube is not arbitrary. So the nanotubical part depends on caps. So if you consider 6-gonal plane lattice on the plane, so similar to graphene sheet. So there are 2 parameters just in the local coordinate, in plane coordinates, and you'll get different kind of nanotube, nanotubical fullerenes. And after that, you glue it up. And the classification was obtained by people from chemistry. So if you have caps of first type, so parameters of nanotube 50, I mean these parameters, these numbers n and m. So n0, it's like this one, 550. And these parameters for second type, for third one, and for fourth one. And of course, if you fix it nanotube and if you fix it caps, so the number of vertices depends of your fixing, and the number of vertices is not arbitrary. And let me give you example of for type 1, for type A. So this case when you have 6 pentagons in one cup and 6 pentagons on another one. So here you have 5, and also exterior is another one. So blue just caps, and white just a part of nanocube. So you look into infinity, something like that.
So is it true that the tube has kind of circumference of 5 sexagons? So it's like its width, its circumference is the same. So it always consists of 5.
You need to glue all together, so something like that.
Yes. Yeah, but it's always 5. I mean, because okay. So it's the same. It's the same pattern in the middle exactly always.
Yes. So this nanotube is completely determined by these parameters.
Okay.
So there are 4 types, and for the type A, everything was studied by chemicists Kovac, Ori, and Falcani. I know Ori, he's a chemist from Italy. He's quite famous in Fourier theory. So they consider this class of graphs, and in this case, the number of vertices always multiply of 10. Divided by 10. So in this case, you can construct such a fullerene, and they calculated the Wiener index. They just gave a explicit formula for Wiener index. So similar results obtained for other types too. So for each class, we know structure of maximal Wiener index fullerene, and we know also value of Wiener index. So these fullerenes are maximal in sense of Wiener index, but they still belong to the class of Pogorelov polyhedral. So we can realize this fullerene as a polyhedron hyperbolic space with all the address angles equal pi over 2. And this recent project with my student Andrei Egorov, this paper which appear very soon, possibly this year, in the Journal of Computational Mathematical Biophysics. And yeah, we discussed relation or correlation between combinatorial parameters and geometrical parameters, so between the Wiener index and hyperbolic volume. So this picture for fullerenes with the 60 vertices. So the famous Buckminster fullerene is belong to this class. It's one of them. But totally, if you consider graphs with 60 vertices, so there are 1,812 such graphs, which are fullerenes with 60 vertices. And we calculated volumes corresponding to these graphs, volumes of their right-angled realization hyperbolic space. And we found that this number of fullerenes give us 1,805 different volumes. And you see there are comparing of hyperbolic volumes and Wiener index. So you can easily observe that if a Wiener index is quite big enough, then volume is small enough. So it's most linear correlation, and the minimal volume fullerenes are those with the maximal Wiener index. In this picture, just for particular class, and we investigated our conjecture about volumes, and we check it for hyperbolic volumes which we already calculated, and we got the following result. This result presented in the table. So we checked that this conjecture is true for graphs up to 64 vertices. So just say me something about this table. For example, the case which I presented in the previous slides correspond to the 60 vertices. So number of fullerenes, number of graphs with this number of atoms, this number of vertex is 1,812, and number of different volumes, 5,005, and 21 is just the smallest among them, and the biggest volume 25. This is among fullerenes, not among all Pogorelov polyhedra. And we know minimal volume fullerenes, and we just check it, caps structure for each of them. So it's A, B, C, D, just exactly caps which appear in the previous slides. So this kind of caps. Okay, and unfortunately, it is difficult to calculate more examples. It's
For 34, for 34, it's a different type that minimizes the volume. It's not one of those tubes, or there are no tubes for 34 vertices.
It's small enough. It's not of such type. Yes.
Okay.
At the beginning, so we started calculation with 20, not with 30. But for 20, there are really structure is too simple. You cannot recognize this. Maybe some generated tube. So we see such a situation. So we see that minimal volume hyperbolic fullerenes are those with the maximal Wiener index. And finally, I just present concrete examples. So if you consider fullerenes with 84 vertices, so the left one is the smallest, is the minimal volume example, and the right one is the maximal volume example. And you see, in some sense, the maximal volume, they are more compact. I mean, they not too close to nanotube. I mean, it's not so long. And if you think about the diameter of the graphs, so distance between the maximal distance between vertices. So usually for maximal volume, diameter is smaller. This observation too. So finally, we see that in the case of hyperbolic polyhedra, where we fix the dihedral angles, everything depends on combinatorics, and properties, geometrical properties as a volume, such as the volume, also depends on combinatorical properties, and Wiener index seems a good parameter to understand geometric structure from combinatorics for this class. Okay, so maybe I stop at this point. Thank you very much.
Thanks a lot. Yeah, it's very intriguing, this last connection. So are there any questions? So I actually, while people are thinking, I actually want, sorry.
Do I take it right that in chemistry there are no idea why you should consider just these two parameters? It is more heuristic than some proof behind it.
Referring to the Wiener index and this parameter P, this distance 3 carbon.
Yeah, to define, for example, the boiling point.
Oh, okay. Maybe I take it just a very particular example of index. So Wiener index, but in our preprint, you can find in our archive, we consider different parameters. So some generalization of Wiener index, some parameter like, for example, distances between pentagons in dual graphs, and also we compared correlation of hyperbolic volume and these topological parameters with Fullerene energy.
But I think Grisha meant from chemical point of view, this temperature for paraffin boiling. So you gave us this formula that depends on two graph parameters.
Yes.
Grisha, I think, was asking what kind of justification or what kind of explanation does this formula have, or is it just heuristics?
I'm not chemist, so it's question not to me, but
Okay.
I know there are a lot of literature about Wiener index.
Okay. And is this polarity actually well understood for fullerenes? because I guess if one wants to figure out how does this boiling point behave, then it's natural, okay, to understand the Wiener index, but also the polarity. Do you know anything about that? And does it have actually any meaning for the polytopes?
I should say that there are a lot of papers about Wiener index, and there are a lot of generalizations. So I showed you only just basic ideas, so how Wiener produces it. But now there are a lot of results about properties of the index. For example, it's take values by modular 8, something, so many results. And also people from chemistry works in this direction too. So, for example, we put the preprint, which is the last one. So when we put this preprint in archive, the paper was already accepted. But I got the letter from my colleagues from chemical informatics. They invited to submit to their journals. So it looks interesting for them.
Okay. I also wanted to ask you, can you maybe say a few words again about how do you calculate this volume, or because you said something, but I'm not sure that. Yeah, like what combinatorial parameters go into this calculation of the volume? Just to understand better the possible relations with this Wiener index.
So in hyperbolic geometry, we usually use the Lobachevsky function. So it's almost the function which was used by Lobachevsky in the 19th century. And this function looks quite complicated. I mean, this kind of d-logarithm function. And for example, in this paper written by John Milner, you can find formula for tetrahedrons, for how to find the volume of a tetrahedron if you know dihedral angles. And this formula is quite complicated. And also in the case of dodecahedron and its generalization, this formula doesn't look easy. So in most cases, we are able only calculate up to few digits. And for arbitrary polyhedron, idea is as following. So you have a polyhedron and you consider triangulation in simplices. You need to calculate parameters of these simplices, and after that you use Lobachevsky function. And it's not very stable. I mean, we use it some method, and so many things depends of initial point because we use Newton approximation in standard way. And in hyperbolic geometry, there are a few very good computer projects. One of them is called SnapPeer. So it's a software which give you possibility to calculate parameters of hyperbolic manifolds, like volumes, geodesics, and also invariance of knots or manifolds. And inside this program, you can calculate volumes, but just up to the best results up to 50 digits. And it's, for example, there are still open problem in theory of three-dimensional hyperbolic manifolds. If there is a pair of two hyperbolic three-dimensional manifolds such that rate of their volumes is a rational number. So if you have two manifolds and one is the covering of another one, so ratio of volumes is integer. So now you can take one manifold covered by two different ones. So you can get volumes with the rational rate of volumes. But since we calculate just up to some digits, it's still open problem posted by Mikhail Gromov in 78, I suppose, if there exists a pair of manifolds with irrational rate of volumes. It's quite a complicated question.
Okay.
So in all examples which I presented to you, I demonstrated only first 6 digits.
Okay, so basically we have very little understanding of how to calculate these volumes. So just for tetrahedron, essentially. some simple polytopes, and then approximate. Okay.
And if we return to Pogorelov polyhedra, is there any good way to calculate what happens with the volume when we use our operations?
We can just control if volume increase or decrease. I mean, the result is the following. If you use these operations, so if you decompose, you can control that volume decrease. So, for example, if you consider operation which is the composition, so you have one polyhedra and another polyhedra. They're just combinatorial polyhedra. And you construct the new one, just a union of two. But it doesn't mean, it's no guarantee that you get a union in geometrical sense.
Certainly.
So you can just understand that the volume decrease or increase. And as I know, there are no nice estimates how it change.
Okay.
Any more questions? Okay.
And is there any hope that there exists some relations, or it seems that there must be some relation between the volume of initial polyhedra and the result of operation?
So, as I told, you can decompose is a union of legal polyhedra. So you cut and you remove edges, and finally you get legal polyhedra, and they look like this one. So for any of them, I have a volume formula, depending on n. For these species, we have a formula, given in terms of Lobachevsky function. So you can approximate as far as you want. But if you construct more complicated guys, for maybe like something like that one, so I know that the volume increase after this age in age, but unfortunately it's not easy to control it. Okay.
So when you, which means that if you work with fullerenes again, then of course this operation takes you out of the class of fullerenes one. You cannot.
It is inside the class of fullerenes. No, not always. Sorry, not always. Yes.
Not always. It looks like it. So is the so if one wants to prove this Wiener index result or something about this, is there any hope to say that a combination of two operations, like kind of on neighboring faces or something like that, increases volume? So you perform two consecutive operations, do some kind of switching, I don't know, and then you say that this operation also increases volume, or some statement of this kind, or maybe reformulating how complicated is this, how combinatorial is this proof that certain operations increase the volume, that we know that certain operations increase and certain operations decrease the volume. Is it very combinatorial, or what kind of things does it use? Kind of the answer to the previous question, that you have this relation between, is it very combinatorial or not quite?
I don't see that considering the Wiener index is a good way to obtain results about hyperbolic volumes. I mean, I just observed the correlation between these parameters.
Yeah.
I'm not sure that Wiener index gives some approach, because it's related to interior distance in graph. So Wiener index is just a number of edges. It's not related to metric or hyperbolic space.
Yeah, I was just of course saying hypothetically that maybe there is also a certain operation which is combination of these two basic operation, which also can be proved to increase the volume, and then you can try to get more kind of information on how the volumes are ordered with respect to each other. So can you repeat maybe about this part about the relationship between the volumes, this P1 greater than etc. Pk, this part, and when these operations increase the volume? Yeah, this thing. It's.
So if you add a new edge, the volume increase. If
you add a new edge, volume increase, and that's.
So imagine like this one. So it was just look at this picture. It was a plane, signal plane.
Okay.
And now you have some wedge over this plane. So it's collapsed to the.
Okay, so it is really simple. It is really very simple.
Yes.
Okay. And then of course when you glue two polytopes, the volume also increases.
Yeah. So give us some intuition, but don't give us explicit formulas.
Any other questions? If not, thank you very much again for this talk. That was surprisingly very combinatorial, at least surprisingly for me. And it's very interesting. Maybe some people would be interested in working on this. There is a couple of actually people attended the talk that work on this Wiener index in recent
very nice.
months. So yeah,
thank you very much.
We'll lead somewhere. Thank you. Thanks a lot, and bye bye everybody.
If you have any questions or suggestions, just contact by email. So.
Okay, great.
Yeah, thank you very much.
Bye bye.
Thank you.
Yeah.